Hi everyone. In the last few classes, Hi everyone. In the last few lectures, we have discussed about the spectral representation of compact self-adjoint operators as well as compact normal operators. Today we are going to discuss about the singular value decomposition and some important properties of compact operators. So let us quickly recall. If A is a m by n matrix, A is a n by n matrix, then A can be written as U lambda V, where U and V are unitary matrices and lambda is a diagonal matrix with diagonal entries as S1, S2, so on, Sn. It's a diagonal matrix, and eigenvalues of mod A are square root of A star A are exactly the numbers S1, S2, Sn. So Sj is the jth eigenvalue of A star A power of, and we know that is nothing but modulus of A, and these Sj's are known as singular values of A. S1, S2, so on, they are known as singular values of A. They are eigenvalues of mod A, but they are known as singular values of A. So this representation or decomposition we call as singular value representation or decomposition for A. We know that A is diagonalizable if and only if A is normal. But here if A is any n by n matrix, we can write A as U lambda V, where lambda is a diagonal matrix with diagonal entries S1, S2, so on, Sn. Now we want to actually generalize this result to the infinite dimensional setting, SVD, for compact operators. Okay. Now let us take T to be a compact operator defined on H. In fact, we can take T to be a compact operator from H1 into H2 and do the same procedure. Then we know that mod T is also compact. This is square root of T star T. This is compact. And we know that mod T is also positive. So we can apply the spectral theorem for mod T and write down the spectral representation for it. So let us by the spectral theorem. So mod T x is nothing but summation n equal to 1 to infinity Sn inner product x phi n multiplied by phi n for every x in H, where Sn's are mod T phi n is Sn phi n for every n in n. That means phi n's are eigenvectors corresponding to eigenvalues Sn of mod T, and this phi n is an orthonormal system. Is an orthonormal system for H, and Sn is sequence of eigenvalues for mod T. So Sn converges to 0 as n tends to infinity if Sn is infinite. And we know that the representation of mod T given here on the right hand side the series of operator converges to mod t in the operator NOC. Now let us look at the polar decomposition of t. Let t equal to v mod t be the polar decomposition of t, and we know that null space of v and null space of mod t, and that equal to null space of t. So in the earlier representation of mod t, so mod t phi n equal to Sn phi n, that means phi n's are in range of mod t. So as, and this is anyway subset of range of mod t closure, and this is null space of mod t perp, and we know that null space of mod t and null space of t are same, and this is exactly null space of v perp. And we also know that v restricted to null space of v perp is a map from null space of v perp into h. This is an isometry because it's a partial isometry restricted to the initial space. It is an isometry. Now we can actually say that v of phi n's are coming from null space of v perp. We can say that that forms an orthonormal set in H. So therefore v phi n is an orthonormal set in H. So let us write psi n to be v phi n. Then we can actually write down Tx as v mod Tx, but we know what is the representation of mod Tx. So let us call this as equation star. So by star we can, on polar decomposition, we can say that this can be written as v mod Tx. So this is summation n equal to 1 to infinity Sn inner product x v n multiplied by v phi n, that is nothing but psi n. So this is called the singular value decomposition for t, and this Sn's we call as singular values of t. So they are exactly eigenvalues of mod t. Okay. So this is also known as Schmidt decomposition. Of t. Okay. Now we can have a doubt when when we represented for a matrix, we have written in terms of a diagonal matrix and unitary matrices. But here when we look at compact operator, we are writing in terms of operators only. In fact, we can actually write down this in terms of infinite matrices. So let us look at that part. So we know that mod t is compact, and earlier we have seen that mod t is u star mf u, where u from h to l2 is unitary, and mf is a multiplication operator from l2 into l2 mf at xn element of l2, that is s1 x1 s2 x2 x3 x3 so on for every xn in l2. Here f is nothing but it's a function defined on spectrum of mod t and taking values in R. In fact, here it takes only positive values. because it's a identity map from spectrum of T to R. So here S1, S2, Sn. So Sn goes to the same. Okay, so in this way we can represent mod T as multiplication operator. Now apply the singular value polar decomposition for T. So hence we can say that T equal to V mod T equal to V U star MF U. Now we can write V U star, this operator, as W MF U, and here MF is nothing but it is an infinite matrix with diagonal entries as S1, S2, S3. So it's a diagonal matrix with diagonal entries as S1, S2, S3, so on. Okay. Now here U is unitary, but W need not be unitary because V is a partial isometry. So in particular, if T is 1 to 1, then V is an isometry. Hence we can say that W is an isometry. W become unitary whenever V is unitary, but V become unitary provided T is bijective. But since T is compact, it cannot be bijective unless the domain is finite dimensional. So in that case, it collapses to the earlier case, that is a matrix case. So when H is infinite dimensional case, we cannot get unitary here, but we can get an isometry. And this U is unitary. So this is a singular value decomposition for T when T is compact. Okay. Next we want to look at some more important properties of compact operators. So let us take T to be compact and lambda non-zero, then null space of T minus lambda I is finite dimensional. This result we have proved when T is compact and normal. In particular, when T is self-adjoint and compact, we have shown this result. Now we want to prove this result for general compact operator by dropping the normality condition. So let us look at the proof. Now if you look at T restricted to null space of T minus lambda I, this is a map from null space of T minus lambda I into itself, null space of T minus lambda I. The reason is that null space of T minus lambda I is a closed subspace of H, and this is invariant under T. T of null space of T minus lambda I is contained in null space of T minus lambda. It's an eigenspace corresponding to lambda, so it is invariant under T. Now note that T restricted to null space of T minus lambda I, this is a map scalar times identity, that is lambda times identity on this null space of T minus lambda I. Now restriction of a compact operator to any closed subspace is compact, so this is compact. So this implies that since lambda is non-zero, null space of I minus lambda I, null space of, I am repeating, since lambda times identity is compact, the domain of identity must be finite dimensional. This implies that null space of T minus lambda I is finite dimensional. Okay, so this completes the proof of the result that whenever T is compact, null space of T minus lambda is finite dimensional. Now let us look at one more important property. Let us take T to be compact and lambda to be non-zero. Then we can say that range of T minus lambda I is always closed. Okay. So let us write T minus lambda I by T suffix lambda. We want to show that range of T lambda is closed. So let us look at write A suffix lambda as T lambda restricted to null space of T lambda per. Now it's a map from null space of T lambda per into H. Okay. Also note that range of A lambda is exactly range of T lambda, because the only difference is that T lambda contains null space of T lambda in the domain, but that is mapped to 0 under this map. Hence we can say that range of A lambda is nothing but range of T lambda, and we also know that A lambda is 1 to 1. That can be shown easily. Now if range of T lambda is not closed, then automatically range of A lambda is not closed. Suppose is not closed, then range of A lambda is not closed. Hence we can get a sequence by the characterization of closed range operators. There exists some sequence xn in null space of T lambda per, that is domain of range of A lambda, that is domain of A lambda, with norm xn is 1 for every n in n, such that norm of A lambda xn converges to 0 as n tends to infinity. Or we can say that A lambda xn converges to 0. So this implies T minus lambda I acting on xn converges to 0 as n tends to infinity. Now we know that xn is bounded and T is compact, so Txn has a convergent subsequence. So as T is compact, there exists a subsequence xnk of xn such that Txnk is convergent. But we know that T minus lambda I xn is convergent. Now we know that Txnk is convergent. In particular, T minus lambda I xnk converges to 0. So combining these two observations, we can say that this implies xnk is convergent. So let us say xn converges to x. Then we have Txnk converges to 2x and T minus lambda I xnk converges to Tx minus lambda x, but we know that this is 0. T minus lambda I xnk converges to 0. Therefore Tx equal to lambda x, or we can say that x is in null space of T lambda. But we know that xn is coming from null space of T lambda per, and that is closed subspace. So whenever xnk converges, x must be in xnk must be in null space of T lambda per. So we can say that this is also inside null space of T lambda per. So this is nothing but a 0 space. So or we can say that x equal to 0, but this is a contradiction because norm x is 1. So as norm x is nothing but limit norm x n k, that is 1, because norm x n k is 1 for every nk. So we got a contradiction. We got a contradiction because we assume that range of t lambda is not closed. So we can conclude that range of t lambda is closed. Okay, so these are the two important properties of a compact operator. That is, range of t minus lambda is always closed whenever lambda is non-zero, and null space of t minus lambda is closed whenever lambda is non-zero. Okay. So let us look at one more important property. So if T is compact, then we can say that point spectrum of T is countable. So earlier we have shown that whenever T is compact and normal, then the spectrum is contained in point spectrum of T union 0, and we have shown that the point spectrum is a sequence which is countable. So from that we were able to show that the spectrum itself is countable. So in the general setting also, when T is just compact operator, then also we can show that the spectrum is countable. So this is a starting point to prove that. So let us look at the proof. So here we claim that the non-zero point spectrum is countable. So that means we want to show that point spectrum of T intersection set of all lambda in C such that mod lambda bigger than or equal to epsilon, this is finite for all epsilon positive. Now from this we can write that if you take epsilon to be 1 by n, and spectrum of T you can write countable union of such sets, and if each of the set is finite, then we can conclude that non-zero point spectrum of T is countable, hence point spectrum of T is countable. Okay, suppose this claim is not true. Suppose not. Then there exists an epsilon which is positive and a sequence lambda n in the point spectrum of T with mod lambda n is bigger than epsilon for every n in n, and xn's from the unit sphere of H such that Txn is lambda n xn. Okay. Now xn's are eigenvector corresponding to lambda n. Since lambda n's are distinct, we can conclude that this set x1, x2, so on is linearly independent. Okay. Now let us define Mn as span of first n such vectors x1, x2, so on xn, n is bigger than 1. Then we can conclude that Mn is contained in Mn plus 1. Okay. So by the Ree's lemma, there exists some yn in Mn with norm yn equal to 1 for every n in n, such that distance between yn and mn minus 1 is 1. Here distance attains maximum value 1, But in general, when we have a nonlinear space and if y is any proper subspace, so we can get a vector in the unit sphere of x, the distance between that vector and y is strictly bigger than epsilon, where epsilon between 0 and 1. But here Mn is finite dimensional space, so the distance is the maximum is attained in the ridge lemma. Okay. Now since Yn is coming from Mn, so this implies that Yn can be written as alpha 1 x1 plus alpha 2 x2 plus so on alpha n xn. Hence we can write Tyn is alpha 1, Tx1 is lambda 1 x1 plus alpha 2 lambda 2 x2 plus so on alpha n lambda n xn. So therefore we can say that Tyn minus lambda n yn, we can say that it is, if you look at Tyn minus lambda n yn, you will get alpha 1 lambda 1 minus lambda n x1 so on plus alpha n minus 1 lambda n minus 1 minus lambda n x n minus 1. The last term gets cancelled. So this is an element of m n minus 1. Now let us take m and n are in n with n bigger than m. Then we can actually look at Tyn minus Tym. This we can write as, looking at the same way about Tyn. So let us say this is 1 and this is 2. So as in 2 we can actually compute Tyn minus Tym. So the first 10 terms gets cancelled. You will get alpha m plus 1 lambda m plus 1 x m plus 1 so on alpha n lambda n xn. Now adding and subtracting some terms, we can actually write this as lambda n yn plus z, where z is some element in mn minus 1. So hence if you look at norm of Tyn minus Tym, this is norm of lambda n yn plus z, and this is nothing but mod lambda n norm yn plus z by lambda n. Now this is bigger than mod lambda n yn, this is bigger than distance between yn and m. So distance between yn and mn minus 1, because this is in mn minus 1. And we know that distance between yn and mn minus 1 is exactly 1 by this equation 1. So we can say that this is mod lambda n by 1. But we know that mod lambda n is bigger than epsilon. So from this we can say that, we know that yn is a bounded sequence, norm yn is 1, and Tyn cannot be Cauchy from this one, so Tyn cannot have a convergent subsequence. Cannot have a convergent subsequence. But this is a contradiction to the compactness of T. A contradiction to the compactness of T. So hence we can say that our claim is true Now once the claim is true, we can write non-zero point spectrum is countable union of such sets. So from that we can say that point spectrum of T is countable. Now using this result, we can actually show that the spectrum of T is a countable spectrum of T is countable when T is compact operator. So those details we'll be discussing in the next lecture. I'll stop here. Thank you very much.